All right. Good morning. So today we have lecture number 5 of the course, and this time we're going to start talking about building statistical models around data. So let me give you just a brief overview. Within the scope of the course, we have been talking in the first lectures about designing studies and collecting data. We talked about exploring, visualizing, transforming the data that we collected. And now we're going to start talking about modeling that data. So start making statistical models around the data for different purposes. That's what we're going to talk about today. And so in this lecture, we are going to talk about supervised and unsupervised learning, just a general introduction to what we build statistical models for and what kind of models we build. And then we'll cover 3 basic steps in building models. The first one is how to specify a model, then how we estimate the model given the data, how we make a selection between different models so that we arrive in the end at one final model. And we talked about a couple of very important concepts when building models. One of them is the bias variance trade-off. We're going to see what that is about today, and cross-validation, which is a way of going around certain limitations with the data. So this is going to be the content of today's lecture, and I'd say we just start right ahead with a quick recap of a few statistical concepts. So through the slides today and through the upcoming lectures, you're going to see some notation. Let me just do a very quick recap. When we have a capital letter, something like X, that means a random variable that follows a certain distribution. So that is a certain variable like a height of people or test scores, things like that. They follow a certain distribution over a certain population. And by X, we refer to one of those many different heights or test scores in the population. And then with a lowercase x, in this case, we refer to a particular observation, a particular value. So for example, we could have height equal 170. This would be capital X, and this would be lowercase x. There's something called the expected value, expectation of a random variable, which is essentially the mean. So what is the expected value in the population? That is, what is the mean in the population of that one random variable? So what is, for example, the mean height in the Netherlands? We also have the concept of variance. So how much does it vary? And all the time we're going to be talking about estimating certain statistics. So we talked about estimating the population mean in a couple lectures ago. And today we're going to talk a little bit also about estimating. So whenever you see, remember the hat on top of something, that means we're building an estimate about that something based on data. So we might be able to estimate what is the value of X given a data set. And as we knew, X bar refers to the sample mean. So if we have a certain observations here, we can compute the sample mean of the sample. So like we saw in the previous lectures, one of the things that we typically care about is the mean mu in the population. We can estimate it with the sample mean. Okay, so let's start. We're going to be talking about statistical learning, and from now on, all we're going to do is statistical learning in this course. And statistical learning, you can see it as the intersection between statistics and computer science, and most likely you can think about machine learning. So we do statistical learning to model complex data sets, to build models around complex data sets. And we typically do it for one of 2 purposes. We could do it to try to better understand the data set, try to better understand the data or the phenomena generating the data, trying to better understand whatever it is that we are studying and the data refers to. Or we might be interested in making predictions about that phenomena. So it's not so much about understanding how it works, as much as it is about just making predictions about it, making good predictions about it. So we typically classify statistical learning into different branches. One of them is supervised learning, And the point here is that we want to estimate the output given some inputs. So all the time we're going to have some kind of variables that we can refer to them as the independent variables. And then we want to use them to make a model of the dependent variable. So how do the independent variables affect the dependent variable? And on the other hand, we have unsupervised learning, which is about the relationships and structures in the data. So it's not so much about modeling the relationship between dependent and independent. Specifically in a supervised learning, we don't have any dependent variable. We just have a lot of data, and we want to find some latent or hidden structure and relationships in the data. We will talk about it in a minute. By the way, nowadays, unsupervised learning is usually referred to as self-supervised learning. I'm just using unsupervised for historical reasons. But anyway, you are going to see it nowadays as self-supervised. Let me give you an example. Let's say that we have data about the salary of people, salary of certain employees. So we might be interested in modeling the wage of people. Let's have it here as the y variable as a function of the age, over here as the x variable. So we have here scatter plot. Each of the points refers to one employee. And we might be interested in, again, finding out what the relationship is between those two variables. Now, we might be able to build a model. Let's say this blue line over here is what the model tells us the relationship is between age and wage. And immediately we can see a couple of problems. First of all is that there is a lot of unexplained variability. So the model is predicting this blue line, but any given observation, we see that it's very far away from the prediction of the model, or it can be very far away. So the model is not really good in this respect, in making predictions. There's a lot of unexplained variability in the wage. So what we see is that age alone is probably not a good enough predictor. We are going to need something else, some other variable to try and have a good model of the wage. So what about the year? Maybe we collected the data across different years, and here we have another scatter plot in which we can see the effect of inflation. So we know that the salaries are going to go up every year, or are supposed to go up every year because of inflation. And actually, they kind of do. We see here this positive correlation, very tiny correlation, but anyway, there is, between the wage and the year. So we might include the year as another variable to try to build a model of the wage. And another thing that we know that is affecting the wage is the education level. So whether your studies reach up to primary school, high school, bachelor, master, PhD, we know that the higher the education level, then the higher the salary. So we see it here in this data set, for example, with these box plots. And yes, we might include another variable about the education level to try to build a model about the wage. So in this case, we will be building a model of the wage as a function of the age, the year, and the education level, and potentially some other factors as well. So in supervised learning, this is what we do. We assume there is a certain dependent variable y and p independent variables x. So x1, x2, x3, all the way up to xp. And we want to model the relationship, the function that determines the y given the predictors, given the x's. And this is what supervised learning is about. It's about supervising the learning of this function given the output and the inputs in the data. And typically we refer to two kinds of problems here, either regression or classification. And the difference is essentially in what is the type of this dependent variable y. When the variable is numerical, we talk about regression. So for example, as we were doing, we might be interested in modeling the salary as a function of the age and level of education. In this case, the salary is the dependent variable, it's a number, and therefore this is a regression problem. We might also be interested in, I don't know, modeling the water level according to the weather forecast. So what is going to be the water level? That is a number, therefore this is regression. And on the other hand, we have classification problems in which the dependent variable is actually nominal. So it's something that we cannot attach a number to, or we can, but the numbers are completely arbitrary. So you can think, for example, if we work in a bank and we have the banking profile of different clients, and those will be the X's, the independent variables, and the variable that we want to predict is the accept or reject of, I don't know, a mortgage, for example, whether we accept or reject the mortgage based on the banking profile. You can think, for example, of the problem in which we want to model whether people take the bus, the tram, or the bike based on their socioeconomic status. So we have here the independent variables, and the dependent variable is one of bus, tram, or bike. What transport method do they use? So this is supervised learning. And again, the question is, can we build a model to represent the relationship between independent variables and the one dependent variable? And then depending on the type of the dependent variable, we talk about regression or classification. We have a question saying, do the X values also have to be numbers for regression? No, they don't. And actually, that's something that we're going to cover on the next lecture. So these independent variables can be anything. They can be numbers, they can be categories, anything. All right, so what is unsupervised learning? In unsupervised learning, we don't have any dependent variable, any response Y. There's only X's. So we have a bunch of variables from 1 to P. And the point is to try to estimate some unobserved latent variables Z1 to ZQ, normally with Q being smaller than P. And we call them latent because they are not observed in our data set. If you think about the typical data set or data frame in pandas, so you would have a table with all the observations here in the rows. Then we will have the variables here in the columns. Then the point would be in a supervised learning problem, we have a column representing the response. So we try to build a model. But here in unsupervised learning, we don't have anything. The point is we want to estimate another data frame of variables Z1 to ZQ based on these P variables. And the point is, what kind of variables do we want to find out and for what purpose? And then we refer to two kinds of problems normally, clustering and dimensionality reduction. In clustering, the question is whether we can find one categorical variable that identifies or separates all the observations in different clusters. So the point would be obtaining only one variable Z that would be categorical and represents different groups. So for example, let's say that we have data about how the different cities in the Netherlands use the land surface and their economic activity. And we might be interested in coming up with groups of cities that behave similarly in terms of how they use the land and their activities. So the group here would be the clusters, the group of cities. That would be the categorical variable that puts together cities that behave similarly. Or we might be interested in grouping departments in the university according to different discrimination factors. So what are departments that tend to discriminate against, I don't know, faculty or students in a similar way? So this is clustering. Try to come up with the one categorical variable that we can come up with clusters with. And so the other problem is dimensionality reduction. And the point here is that we want to simplify a data set while retaining information. This is the important point. We want to retain information. So what is the point here? Imagine we have a data set with 1,000 variables, 1,000 X's. That is going to be a very large data set to try to do anything useful with. And so we have techniques to try to reduce that data set to, let's say, 10 variables or 11, 20, 50 variables, something that is a lot smaller, but still retains all the information, all the useful information that we have in those 1,000 variables. And then we're going to see later in the course what are different uses of this dimensionality reduction problem. It could be just to make a supervised learning problem more efficient, or it could be just about coming up with ways of visualizing very complex data sets in a scatter plot, for example. So this is unsupervised learning, and this would be the last part of the course. But today, let's talk about how we specify model. Whether we want to do supervised, unsupervised, or anything, we are going to have to specify what kind of model we want. So let's talk about it. And let's start with this picture we had in the first lectures about any subject of study that we are interested in. So whatever we want to study, whatever process, we can typically represent it as this box in which we have certain inputs and certain outputs. And the process works normally depending on multiple factors. So we have factors that we can observe and control. We as the experimenters or as the people collecting the data, there are certain things that we can control. So for example, which treatment we apply on patients or which algorithm we use for whatever problem we have. We can control temperature, we can control that kind of thing. There are other things that we cannot control, but nonetheless we can observe. So we cannot control, for example, the sex of people. We cannot control their age, but still we are going to be able to measure it. And we know whether a patient, it's a man or a woman, depending on the sex. And then we have unknown factors. So things that we do not know anything about. And actually it turns out that they are also affecting the process in a way that we don't know about. So part of the effect or part of the output here is going to be determined by these unknown factors. And we are just going to miss them, so we are not going to be able to fully explain how the output is computed based on the inputs and the factors. So why is this relevant now? Because we are going to try and build models about reality, about whatever process it is that it's right here and we want to study. So in reality, the phenomena, as we see, works as follows. There is a certain output, let's call it Y again, and it's going to be determined by a certain process, natural or artificial, that depends on factors that we know about and factors that we do not know about. And there's an important distinction here between these two. Now, this is assuming the process is deterministic, otherwise there would be some kind of random error here. But anyway, there's a certain process that depends on the factors. Now, we don't have full knowledge about the process. That is the point. We don't know exactly how it works. We want to understand it. Still, that doesn't mean that we cannot build a model about it. So let's say we want to build a model F, given some observed variables X known. So we have some data about this X known, and we just want to build a model F to try to get the response, the Y. So it's all about trying to make something like this. Building a function F that is going to allow us to compute or estimate what the output is going to be given the known observations. And of course, there's going to be some degree of error, epsilon. Now, that epsilon is going to model two things. First, the fact that this function is, of course, going to be different from reality. It's going to be a model about it, some kind of simplification about the process. But of course, we don't know how the process works. We just have some kind of approximation for it. And the other thing that the epsilon is measuring is the fact that we don't know anything about the unknowns. Our function F is going to be only a function of the known variables. It's not going to be a function of the unknowns. So of course, there's going to be some limitation as to how well this function is going to represent the response. So we have a model of reality, and because it's a model, we know there's going to be some degree of error. And these are the reasons why we have error. Now, of course, we can start saying something like, what is the class of models that we are going to employ? So let's refer to it as capital F. What is the class of models? We're going to see examples now. What is the possible class of models, the possible family of models that we are going to use? And the point is that out of those many possibilities, we are going to come up with the one that F had one estimate of the function from that class of models that is somehow useful to us. For whatever purpose we want to build a model, let's say we want to make a prediction about whether someone is going to default in their credit card or not. We want to build a model that is useful for us for our specific problem. So let's talk about it with a little bit more detail. So suppose we have some output variable Y. And by the way, we also refer to it as the response, dependent variable, target, or outcome. You're going to see these terms interchangeably to refer to y. And let's say we also have p input variables, x1 to xp, which we also refer to as predictors, independent variables, features, covariates, etc. So what is the observed variables? The point is we assume there is a relationship f that is optimal in some way. So there exists some function f that is optimal to refer to the relationship between x and y. And f is going to model the systematic relationship between the dependent variables and the dependent variable. It's going to be fixed. That relationship is going to be constant. It's just that we don't know what it is about. We don't know how it looks like. And then epsilon is the random error term, something that looks random to us. It's going to be independent of the features and normally with no bias. So statistical learning is all about estimating that optimal function. So assuming the class of models F, what is the one estimate that we can have about the one that is optimal? And we are going to do it based on some input data. We have a question, shouldn't the epsilon be a function of certain parameters instead of a constant? No, and actually it should not be a function of anything, because if it's a function of something, that implies that you have a certain knowledge about how it looks like. And the point is that it should be random or look like random to us. We only pose certain constraints, like it should have a zero mean, but that's about it. Now, a different question is whether in your specific model you have a certain pattern for the error for epsilon, but that's something we will talk about it later. It should not be like that, even if it is. We'll talk about it in the next lectures. Okay, so what is a class of models? A class of models, for example, could be something like this. It's just a set of models of certain characteristics, whatever they are. For example, let me refer to F1 as all the linear models that look like this. So we have the response is a function of some parameter plus some variable x1 plus variable x2. So all the linear models of two variables, I'm going to call those F1. Let's say F2 are all the models of the form y is a exponential function of the x. So all the models in which we have these 1, 2, and 3 coefficients, referring to the exponential relationship between x and y. Now we have some data, and a model from the class is one of a specific instantiation from the class. So for example, from F1, we might be interested in this one specific model. So you see, it's something that has the same form as this. It's just that we are using specific coefficients, 2, 4, and minus 1.3. We might have another instance from F1, another instance of all the linear models of two variables, which is something like this. So each of those two would be an instance from F1. And this one here is an instance from F2. It's a model of the form, something like this. We have epsilon, question, epsilon is some probability distribution, right? Yes, there is for one specific observation here, this is actually one value, but normally we care about the distribution of those residuals, of those epsilons. We're going to talk about it later. So this is what we refer to as a class of models, something like a template, if you will, of what a model could be like. So let's say that, for example, reality in whatever problem we're studying looks like this. Of course, we never know about this, but just for illustration here for the lecture. Imagine that the response is a function of two variables, x1 and x2. x2 is categorical, x1 is numerical. And let's say that the true relationship is something like this. This is what reality is about. So there is this positive exponential quadratic relationship, and it's just a difference between two groups, A and B. So this is reality. Now imagine that we make the decision of saying, hey, I only observe x1. Or for whatever reason, we don't know anything about x2. This is an unknown, and we only know about x1. So this is known. Now, the class of models we are going to assume looks something like this. It's a linear model depending on only one input variable x. So in this case, epsilon is going to capture the fact that the class of models does not contain the true model. So this true model, because it depends on two variables, x1 and x2, is not contained in the class of models. So that means that it doesn't matter how good our final model is, it's never going to be the same as the true model because, to begin with, we are not measuring this relevant x2 variable. So whatever we do, there's going to be always some degree of error. And so the optimal model, given just x1, it will be something like this black line over there. That would be the optimal model in our case. This is the best we can do without any knowledge of x2, and without modeling the quadratic relationship. Because you see, in reality, it's a quadratic function of x1, but we are modeling it as a linear function of x1. This is what epsilon is about. It's about the mismatch between the best that we can do and reality. So this is the optimal model, the best that we could do under our assumptions. Let's say that because of domain knowledge, we have a different class of models, and we say this is actually x2, so x1 to the power of 2. Then we could have a better model, but still it would not be reality because we are ignoring x2. So let's see, why do we want to estimate the function anyway? As we said, you might be interested in making predictions or understanding. If we build the models for prediction, then the point is we want to estimate the outcome y for some observed input x1 to xp. So we want to make something like this. We want to estimate that prediction. And if that's everything that you care about, then we typically see as the function as a black box. So that means we don't really care about how complex it is. We don't really care about what features there are, what kind of parameters. We don't care about it. We only care about the y-hat, about the prediction. Is it making good predictions, yes or no? I don't care where the predictions come from. I don't care what kind of features. I don't care how complex they are. I don't care about the relationships. All I care is this, the y-hat. And as we are going to see, there are objective and well-defined measures of the accuracy of a model. So if that's all we care about, how can we quantify how good the model is? And the point is, typically, we try to estimate this function to optimize that measurement of the accuracy of the model. We're going to talk about it later. If, on the other hand, we want to make the model for understanding, then we don't care really about the y-hats. We care about the function. So typically, we see now here f-hat as a white box. So as we had earlier, we have something like this. What we care about now is this. What does it look like? How can we better understand the relationship between x and the y's? So we do care about what's inside and not so much about the accuracy of the predictions. And this is useful for exploratory analysis, for example, because we can see which predictors are associated with the response, or which predictors are the most important to determine the effect in the response, or what is the relationship among the multiple variables. So this is what building models for understanding is going to allow us to do, try to better understand the phenomena, the underlying phenomena under the data. And so it's all about what you want to do. You want to make predictions, or do you want to understand? Sorry, as you see, I'm coughing all the time. So depending on the goal, the point is we are going to use different techniques to estimate the model. If we care about prediction, again, we rarely look at how complex the model is. We don't really care. Although I have to say, for the past few years, there's a lot of research, a lot of people interested in trying to explain how the models behave. So yes, it's okay if the model is very complex, but still we should be able to explain why is it making one prediction? Why is it predicting A or B? And then if we focus on understanding, we tend to use simpler models just because they're easier to explore and easier to understand. Of course, you can try to make a very complex model to try to understand it, but it's going to be next to impossible. So we typically favor here the simpler models. Now, in this specific course, we're going to focus on the simpler models because we are interested rather in understanding the data, in understanding relationships, and into looking how can we better answer certain research questions. So in this course, again, we're going to focus on the simpler models with quick introductions to the more complex ones. And this leads to the concept of reducible versus irreducible error. So let's assume that we are working on a regression problem. So the response is numeric. And then we are interested in the expected value of the distance between a observation and our estimation for that observation. So the difference between the true value and what the model says the true value should be. So of course we want this to be small. We are here looking at the distance between what the model says and what the model should have said. If we do a little bit of math, we end up with these two terms, the one in blue and the one in pink, in purple. So the one in blue, which is measuring, you see the difference between the optimal function and our estimate of the function, this is what we call the reducible error. And the point of the reducible error is that it can be minimized by choosing a better model from the class or better predictors. And we have this blue error term, the reducible error, because in general, our estimate is not going to be optimal. We are going to see why it's not optimal later, because it's based on data. And so this reducible error still is going to be in there, but we can try and minimize it by making a better decision about the class of models or using different features. This is what statistical learning is about trying to get as close as possible to the optimal function. And then here in purple, we have the irreducible error, which you see it contains it pertains to epsilon. And this irreducible error, it represents an upper bound on how good the model can be. And it again stems from the fact that the optimal function still is going to be different from reality, and that we do not know all the factors affecting the response. And this is why the study design is important. This is why the first 3 lectures are important, because regardless of how much data you have, regardless of how complex the models are or how complex the training process and everything is, you are always going to have some degree of irreducible error. And the only way to get better at irreducible error is to better understand the process, to get more knowledge about it, and to make sure that you measure all the relevant variables in your study. If you don't measure everything that is relevant, you're going to have a high irreducible error. And it doesn't matter what fancy statistics you do, you are going to be able to reduce this error, but not this one. So this is why it's important to have a good study design, to not just collect data and look at it to try to answer a question. You have to have the right data for it. So let's see the difference again. So imagine we go to the previous example in which we had this reality that depends on x1 quadratically and x2 as a categorical variable. And again, we make a simple assumption about the class of models we're going to use. And in this case, it's going to be, again, a linear model of x1. So here in black, again, we have the optimal model. So what happens? Imagine we collect some data. Here we have these observations, these points. And we build a model that is optimal in a certain sense, given this data. So let's say the model looks like this. Our estimate of the model is a function of x1, and these are the coefficients that minimize certain error or maximize the accuracy of the model in a certain way. As we know, this model does not have any knowledge of x2, so it's going to be just this straight line going through the observations. This is the best we can do. If we don't have any knowledge about x2, that's it. So given this data set, these specifically 30 observations, this is the model that we come up with. Now, of course, we know that there's variation between samples. If I have a different set of data, let's say these other 28 points, then the model is going to be slightly different. And if we have another set of points, let's say 37, the model is still slightly different. It looks similar, we see, but the actual model is different. And if we sample another set of points, let's say 37, then we have a different model. So you see here we have 4 replications of the same study, and in each of them we build a model. You see the model is different because we have different data, of course. So maybe looking at this, we figure out we are missing something. We are missing a quadratic relationship. So instead of assuming this class of models, what happens if we assume a quadratic relationship? So now there is this x1 square. What happens? Well, with the same data we had before, this is the model that we build, and we see now the relationship between x1 and y looks a lot better. Now it's capturing this quadratic nature of the relationship, and so on and so forth for the other 4 data sets. So the point is, here is some degree of error that we are never going to be able to get rid of because we don't have knowledge of x2, right? You see that here. We are never going to be able to get rid of this error because it would require for us to know about x2. However, in this other case, we also have the error that brings us to the point of model a quadratic relationship as a line, and that introduces a certain degree of error that we can reduce. So going from the linear models to the quadratic models is going to allow us to reduce the error, but still, because we do not have x2, we are going to have this irreducible error anyway. So this is just an example of the difference between reducible and irreducible. And nothing better than this quote. All models are wrong, but some are useful. So yes, we know that both models are wrong, but hey, maybe the second model is useful for us for whatever reason, for whatever actual problem we're working on. Maybe just the quadratic model that we saw is good enough for our purposes, so that's fine. It's not about having a model of reality, a very faithful model of reality. It's about having a model that is useful, and that is the point. So just assume that your model is going to be just a simplification of reality. You know, get along with it and just try to see how you can make it the best that you can given the data and the knowledge that you have. And maybe that model is good enough. So again, the point is, if this is reality, something that we don't know about, if this was the optimal model, something that, again, we don't know about, but we know it's going to be aligned because we are assuming a linear model. The point is we can build many different models. Each of those lines is one valid model from the class. So how do we choose one? That is the point. Okay, we make the assumption. How do we actually choose the estimate? How do we choose f hat? That brings us to model estimation. Let me see here. We have a question. So in reality, would you just try loads of model functions and then choose the one which minimizes the error? I would say if all you care about is the predictions, then actually yes, and this is what many people do. Just try many different things. If what you want to do is try to better understand the data or to answer specific research questions, then you don't do that. You focus on the more simpler models and you check those models, and that's it. We're going to talk about it later. So how do we choose one model? How do we choose one function? So the thing is that we have some data, what we call training data, the data that we use to train the model. And it usually consists of tuples of this form. So we have the response and the features for the first observation, all the way up to n different observations. So if you look at it in a table format, again, here we would have y, x1 all the way up to xp, and we have a total of n observations. So each of those observations, by the way, we also call examples, instances. We have different names for it. So the rows of the table, if you will. So the point is we have certain data, a data set. We run our study, and this is the data that we have. With that data, we can build this estimate of the optimal function. We assume a certain class of models, like we saw, a quadratic model of only one variable, for example. And then it's about choosing the function that best fits the training data. So which is the one that is optimal for this training data. And building the function, by the way, is also called fitting the function, training, learning, adjusting. There's different names for it. And the point is, what do we mean by best? So what is the criterion specifically that we follow in order to determine that one is the best model given the training data? It depends on the specific problem. It depends on whether you do regression or classification. We're going to talk about it in the coming weeks. But let's assume there is a certain way of choosing the best out of multiple options. And even though the process is data-driven, because we build a model that is optimal for the data, of course, domain knowledge is going to be leveraged in a certain way. For example, by choosing a good class of models or by knowing which predictors should you include in your study. So domain knowledge is always important, regardless of how complex the training process is, how fancy the statistics are. Domain knowledge is always going to be the best thing that you can leverage. So there's something called nearest neighbors. It's just a very simple example of how to build a model around data. And the thing is that the function that we learn is essentially computing the mean value of the response in the neighborhood of the features. So this is what we have here in the neighborhood. So let me give you just an example. So imagine here we have the response and we only have one input variable, one feature. And we are asking about the estimation of the model for x = 4. So what we're asking is what is f of 4? Then what we do is come around here to the training data. Each of these points represents an observation in the training data. Then what we do is determine what is the neighborhood of the point. So what are the observations that are around this neighborhood? And let's say we say it's those observations in there. Then we get all of those in the training data, compute the mean response for those variables, for those observations, and that would be our output. So this is what the nearest neighbors does. Just choose the nearest ones, compute the mean response, and that would be our prediction. So you see, this is a very simple way of building a model around data. Just, hey, give you the average of similar points in the feature space. The problem is nearest neighbors works kind of reasonably well for problems in which we don't have a lot of variables, or if we have a lot of training data. Still, it's going to be hard to interpret the model because you basically do not have any relationship, any specific explicit relationship between the features and the response. But maybe this model is good enough for prediction. The problem is, again, when the number of features is very large or the data set is small, then we are not going to cover the full p-dimensional space. So if you think about it, having p features determines a p-dimensional space. And the point is that the training set normally does not cover that full dimensional space. So by the time that we want to make a prediction here with this function, the selection of neighbors actually might lead to a selection of closest points anyway that are very far away in the feature space. Because again, it's going to be very, very difficult to have closed points everywhere in the feature space. If you think about something like this, then yeah, only one feature is not going to be so much of a problem. Although you might think, what happens if we are asking for f hat of 10? We don't have any data around, I don't know, x = 10 could be around here. We don't have any data about what happens here in the training set. So how are we going to make a prediction for x = 10? Well, it's about the same. Choose the closest data, and that would be your prediction, given those observations there. But you see, it's not going to be a good prediction because we don't know anything about what happens here. We don't have any explicit relationship between x and y. And this problem is going to be only worse when we talk about many features, about high dimensional space. So the point is we need another class of models, something different, something that incorporates structure in a functional form, something that explicitly tells us what's the relationship between x and y. And this is what the course is going to be about. So we have, regardless of the type of problem, we categorize the models, the methods that we use in two kinds, depending on their functional form. So on the one hand, we have parametric models. Those are the ones that assume a certain class of models defined by a fixed set of parameters. So for example, if we have y equal one coefficient plus another coefficient of x1 plus another coefficient of x2, we have a fixed functional form. So we have one coefficient, two coefficients, three coefficients. That's it. There's a fixed set of parameters. And the point here would be to fit or estimate what are the parameters that are optimal in a certain way or in a certain sense for the training data. So what are the coefficients that best describe the training data? That would be the point of the parametric model. And then we have non-parametric models. Those are ones that still assume a certain class of models, but it's very relaxed. It's very simple. There are very few assumptions about how it looks like. The point is that the number of parameters, it's usually proportional to the size of the training set. So it's usually something like k nearest neighbors. It's something about taking the full data that we have and then compute something with all the observations in order to make a prediction. So this is what a non-parametric model is. It's something in which the number of parameters normally is proportional to the size of the training set. So again, in a parametric model, here we have a new observation, we have a new value for x1, a new value for x2, we just plug the numbers into the formula, and that's it. Here in a non-parametric model, we would have to compute something with all the training data normally. That's the difference between the two. The difference is that the non-parametric models are more flexible. They are more expensive, more complex, but they are more flexible. So let me here give you an example. Imagine that we are again modeling the wage, or actually this is income of a certain person by years of education and by the seniority in a company. And let's assume the true model looks something like this. We have all the observations in this three-dimensional space. That's what it looks like. A parametric model, for example, would be a plane, something like here in yellow. Just a plane in that three-dimensional space, and that is the model. So for any given value of years of education and seniority, for example, we go to the point in that plane, and that will be our prediction, our estimate for the income. So you see the model is not very flexible, but hey, maybe it's good enough. The point is it's not flexible, it's just going to be flat, so to speak. If we do a non-parametric model, we might be able to accommodate better to the training data. You see, we might have this bump around here. We have a model that wiggles a little bit more in the dimensional space. And maybe this is better. Or maybe this is the level of complexity that we need for a specific problem. So this is the difference between parametric and non-parametric models. And this is important because of the concept of overfitting. I think we are going to stop here. We're going to have a break, and then I continue precisely here with overfitting. So it's 11:36. Let's come at I don't know, 10 to 12. Let's come back at 10 to 12, and then we continue with the rest of the lecture. See you in a minute. Of course, feel free to post any questions that you have, and I'll try to answer them now. All right, we're back. We were talking about uh, the complexity of models. So how we can build the parametric models of an arbitrary complexity, because here we were talking about only 2 features, but we could talk about hundreds of features. And we could talk about different transformations of the same features to build an even larger model. We can build a non-parametric model, which essentially has many different parameters. So you see, we could potentially, for this case, for this specific problem of the income as a function of year certification and seniority, we could potentially build an arbitrarily complex model just to try to go through each of the observations that we have in the data set. And that would lead to the problem of overfitting, because in general, we can obtain a better fit to the data just by allowing more flexibility in the model. And see that I'm here having quotes for just. So that just is not so simple many times, but only by allowing more flexibility in the model, only by, for example, allowing more parameters in the model, we could in principle obtain always a better fit to the training data. It's just about making the model more complex, more flexible. Again, this often translates into adding more parameters. And at some point, what I want you to see is that we will have a near perfect fit to the training data, a model that almost perfectly or perfectly fits the training data. But the model will not be any good beyond the training data. It will not be a good model of reality. It will be a perfect model for the training data that we have at hand, but it will not be a good model for reality. Why? Because it kind of remembers the instances in the training data. That's what we're building, a model of the training data, but it doesn't learn the underlying patterns. It doesn't learn the underlying relationships between the variables. So if we try to use it to make predictions on unseen data, on new data, it's going to fail. Or if we try to use that model to try to answer questions about the population of interest, it's going to fail because it's going to be a good model of the sample of the training data, but not a good model of reality of the population. And also, if the model is too complex, it's going to be near impossible to try to understand it. So it's about finding the sweet spot with what is the appropriate model complexity such that we can still have something about the population, something about the underlying pattern. So in this case, I'm showing you what an overfitted model is. It's one that if you see goes exactly through all the observations. It just goes up and down specifically in a certain way to accommodate all the observations in the training data set. But this is not a good model of reality. Or maybe it's just easier if we visualize it like this. Imagine we have only 2 variables and we have observations that do something like this. Probably a model that looks kind of okay is something like this. But you can always build a model that does exactly this or that. And of course, that would be a model that is completely useless. It's not a model anywhere close to reality, but hey, it's a model that goes perfectly through all the observations. It's an overfitted model. So the point is, we may come up with many different models, as we suggested earlier in a question. So how do we select from those? And then we get into the concept of model accuracy. So imagine that we fitted some model, some F hat, given the training data. The question is, how adequate is it? How good is it? What we refer to as the goodness of fit. So the answer depends on how we measure it. How do we measure the accuracy of the model? Let's say that we measure it with a certain function A. So A is going to be a function of the model. And so the point is, how do we quantify that? Think, for example, if we're working on a regression problem, maybe what we want to look at is the magnitude of the errors. So if you have a regression problem, something like this, throughout the observations, we might be interested in this magnitude. So how large is the difference? Sorry. So how large is the difference? If we work on a classification problem, Maybe what we're interested in is how often do we misclassify an observation. So you say it depends on the problem, and actually depending also on the specific classification problem, you might be interested in penalizing some misclassifications more than others, things like that. But in general, let's say there is a function A that we can compute given the model. And so if we use the training data, let's call it TR, the training data we know contains n observations of the response and the independent variables. And in principle, we could compute what is the accuracy of the function given the training data. So we could see in this training data how large are the errors or how often do we misclassify in this specific training data. We can always compute this. But what we see is that the model can be arbitrarily good. We can overfit the model. So this accuracy can get arbitrarily good in the training data. So it's not really a good measure of how well the model performs. Ideally, we would test on new test data, unseen observations, something that the model did not know anything about when we were training the model. And so ideally, we would test the model on new observations that are not part of the training data, so that we can estimate what is the accuracy of the model in general, in the population of interest for all possible data that we could use in the model. And it's important that these test data, these test observations, are sampled from the same population as the training data, because otherwise we would be kind of, imagine, building the model in France and then testing the model in the Netherlands. That doesn't make sense. We should sample the training data and the test data from the same population. And ideally, it would contain all the other elements of the population. So imagine that we build a model for the height of the people in the Netherlands as a function of, I don't know, the weight and the age. Then we have a training data of 1,000 people. We build a model. How well does the model perform? Well, ideally, we would like to know it by testing on the other millions of people that we did not use for training the model. That would be an ideal case. That, of course, is never going to happen. But you get the concept of this difference between the training data we use to train the model and then the test data that we should use to try and estimate how well the model works. And the point is, you should always try to test on data that was unseen by the model during the training process, because otherwise we could be falling for overfitting. So the point is, we have the training data set, whatever data we collected, we fit the model, we come up with this estimate f hat, and we can always check the accuracy of the model for the training data. This is something we can always do. It can be improved by choosing a better class of models, a better set of features, etc. But we know we can overfit. So we can use this anyway to try to see what is an appropriate model, what is an appropriate class of models, for example. But then we should always test on new data, test data. We get the same model and we check the accuracy. And that is going to give us an estimation for how good the model is, how is the true capability of the model on unseen data, on the population. Those are two different things. Again, this one can get arbitrarily good, but not this one. And we're going to see an example right now. So imagine, here we have the problem in which we try to model y as a function of x. Each of the points corresponds to one observation in the training data. And in black, we have the true model. Of course, this is something that we never know, but again, only for illustration purposes, let's pretend this is the true model. And we see that, of course, there is some degree of irreducible error because this model is only accounting for one feature. So ideally, we would like to get something like the black model. So given the training data, we may build a model that is too simple, that is overly simple for the reality. So that model is going to be here in orange. It's the straight line. So you see, this is a very simple model because it should have this kind of quadratic shape. But if we assume that it's a line, we fit the line, this is the one that is optimal, we can compute the accuracy. In blue, we have a model that is a little bit more complex, and it's just okay. So it's a model that is very similar to the black one with some differences over here and some differences over here specifically. And then in green, we have a model that is overly complex. It's too complex. It's overfitted to the data. And you see that it wiggles a lot, trying to accommodate the training data set, but it's too complicated. So here on the right, what we're doing is measuring the accuracy of the model. And specifically, we're measuring in terms of the squared error. So the squared deviation between the prediction of the model and the true observation in the training data. So actually what we want to do is have this one lower, have a model with low error. And here we have a measurement of the flexibility of each of these three models, right? So what we have is in gray, the accuracy of the model, so the mean square error of the model in the training data. This is something that can get arbitrarily low. And as we see, as we increase the flexibility of the model, as we allow it to be more complex, we are decreasing the error. And specifically here we have the orange model, the one that was too simple. It has too much error, is not very flexible, and therefore it has a high error. Here in green, we have the opposite. We have a model that is very flexible, but is also is reducing the error a lot in the training data. And somewhere in the middle, we have the blue model, the one that was just kind of okay. However, if we look at how the model performs on unseen data, on data that it never that was never seen during the training process, so something that it tells us how well the model truly behaves for the population of data, then we look here at the red line. And what we see is that, yes, the orange model has a high error, the blue model has the lowest error of the three, and the green model has higher error. Why? Because it was overfitted to the training data. It was minimizing the error in the training data so much that it became actually a poorly performing model on unseen data. So the sweet spot here is the blue model, the one that minimizes the error in both training and testing. We can have a model that has a high error on both. That's a very simple model. Or we could have a model that is overfit. It has a very low error on training, but a high error on testing. So this is a model that is not useful. And by the way, here in the dashed line represents the irreducible error. So this is the best we could possibly do. So here we see the difference between training error and test error or accuracy. Let's see another example. Here we have essentially the same thing, a model that is simple, the orange one, the line, it's actually quite okay because the reality is almost a straight line. Then we have the blue model that is a little bit, twisted. It's not a straight line, and it's also an okay model. And then we have again in green, the model that wiggles a lot, and it's a model that is overfit. So in this case, both the orange and the blue one are kind of okay. If we look here at the error, we see again error decreases as we increase the flexibility. So of course, the green model is going to be better for the specific sample of data in the training set, but it's going to have a very high error in the test set. It's going to be a very bad model of reality, a very bad model for the true data for the population. And in practice, either one of those two would be an okay model. They're okay. They're not having a lot of error in the training set, and they are kind of okay for the test data for the population. So you see, it's not always that the simple model is the worst. Sometimes a simple model is just fine. Again, all models are wrong, but some are useful. And keep in mind that your model is just going to be a simplification again. It's just about which model is useful for you. Here, the orange and the blue ones are wrong, but they're good. The green model is also wrong, but it's also totally useless because it's not a good model of reality. And so minimizing the error on the training set, again, is easy. We could just all try to overfit, try to use more features, transform the features, more fancy models, but that could lead to a high error on a test set, on a hypothetical test set representing the population. And so the thing is that the train error, it can always be computed on the training data. We can always compute this because we do have the training data, but the test error is unknown. We don't know what the rest of the population looks like. We don't know what that unseen data is. We don't have it. It's usually unavailable to us. We don't have any other data than the training set. And so what do we do in these cases? Because it's important, again, that the test set is different from the training model, that we test on data that is different from the data we use for training. But if we don't have it, what do we do? This is important, again, because of this concept, bias variance trade-off. Imagine that we build a model, or we have a class of models. We can fit the models to certain training data. We have to consider two kinds of or two terms in the composition of the error again: bias and variance. If we have something like we did before, we knew we had this reducible error and the irreducible error, and it turns out that this reducible error can be further decomposed into these two terms. One is the bias and one is the variance. One is the bias of our model. So in general, how biased the model is. And the other one is the variance. So how much variability do we have in the model? Let me explain a little bit better. So bias refers to the inability of the model to model the underlying process, right? So it can be reduced by having a higher model complexity. So is the model good or not for the data? Does it have a lot of error? Yes or no? And then the variance refers to how variable the estimate of the model is with respect to the training data. So if I give you one data set and you fit the model, is it very different from the model that you would have fitted with a different training data set? So how much variability do we have in the actual model as a function of the training data? Does it vary too much? Does it depend so much on the training data? Yes or no? And what we know is that complex models are going to depend a lot on the training data. So which specific F hat you choose depends a lot on the training data. And we know that the variance is also reduced by the size of the data sets. So if you have very large data sets, then the variance is going to be reduced. So let me give you an example again. Remember this picture? We used it for something different, but we can use it here again. So we have towards the top low variance, so models that don't vary too much. And here we have high variance. And then we have low bias, models that are having low error, and models that have high error on the left. So each of these points represents one model trained on one training data set. So we are able to fit different models on different data sets. Now, if we have a model that depends a lot on the training data set, so on which specific training data we have, then we are down here in these two with high variance. So the model is very different depending on which specific training data set we use. That's bad. We don't want that to happen. We want to have a model or a certain training procedure that is robust to the training data. And it could also be the case that the model has a high bias, like in here. So maybe you have a low variance. The model doesn't change too much depending on the training data set, but still it's a bad model because it's making too much error. That's something that we could have in here. Or over there, we have a model that varies a lot, but on average, it's making very low errors. It's right in the middle on the bullseye. So the concept of overfitting is actually in here. When we have a model with a very low bias, so on average, the model is predicting very well the training data, but it's going to depend a lot on which specific training data set you have. And we also have the concept of underfitting, which is kind of the opposite. It's the case in which the models are so simple that they don't vary too much. For any given training data set, you're going to have basically the same model, but there is a lot of error in the model. The model is not going to be able to really model reality. And so here we have an illustration of what overfitting is and what underfitting is. It's all about the trade-off between bias and variance. And we call it a trade-off because when one goes up, the other one normally goes down. So imagine again, here we have this example from earlier, and we are now going to plot the variance and the bias of the model. So as a function of flexibility, again, something that we can make arbitrarily higher. We can make more and more complex models. What we're going to have is that the bias, so how good the model is for the training data, is going to decrease. In this case, we were plotting the error. Well, actually, never mind. We're plotting the bias. So the bias is going to be low. The model is going to get better and better and better and better as we make it more complex. However, the variance is going to be higher. It's going to get higher with more complex models because it depends a lot on the training data. So for any given data set, you're going to have a completely different model. That is going to be very good for the training set, but it's going to be bad in general. And that is what's reflected here in the test set. So normally you would like to choose something that is the sweet spot, something that is giving you low bias, low variance, and it doesn't go high in either direction. And normally that's going to be around here. In this point, that's where we will have the optimal model, the one that is having a low bias and a low variance. Anywhere to the left is going to have a high bias. Anywhere to the right is going to have a high variance. So this is the sweet spot. So the problem is, how do we figure out what the sweet spot is going to be? Because again, as we make different models, more complex models, we are going to be increasing bias or variance, one of the two. So how do we figure out what the sweet spot is? Here we have the other example of the basically linear model. And what we saw is that essentially anywhere around here, you would make a good selection because the bias is low, the variance doesn't increase very much. So anywhere around here, you would be kind of okay. But how do we figure that out? So again, as we increase the model complexity, the training error can get arbitrarily low. We know the test error is going to go down until we reach the sweet spot. Beyond that, we are just overfitting, and the test error is going to get high. And same thing is visualized here with bias and variance. The bias is going to get arbitrarily low, but we know that we will be overfitting and the variance is going to get high. How do we find that sweet spot? Well, we could do it with something called cross-validation. And the thing is that in some cases, we do have an actual test set. We do have two data sets for our problem, one for training and one for testing. And this is actually predefined for us. So we can make the two, we can use the two of them. So let's say we have a test set of a certain size M. And normally it's going to be much more than the training data. We use a lot of data for training the model, not so much data for testing. And if we are able to compute the accuracy of the model on the test set, then we use it as an estimate for the accuracy of the model on the population, on all data. That is the point. We train the model on the training data, and then we test the model on the test set, and that's going to be our estimate for how well the model works. Fine. The problem is, very often we don't have test data because, hey, obtaining data is expensive. Many times we don't have it. So how can we go around this limitation? How can we use the training data alone to make a good decision about the model, such as this one? This is what cross-validation is about. And the general idea is that we're going to refit the model multiple times under different subsamples of the training data. And the general principle is we randomly partition the training data in two subsets. And then we use the first one, what we call the training set, to fit the model. And the remaining part, what we call the validation set, is going to be used to test the performance of the model. So it will be used kind of as a test set. Then we do this multiple times and refine the model and see how well the model behaves and make decisions about the model. So let me give you more intuition about it. Let's say this is all the available data we have, all N observations. What we do is split it randomly in two parts. One we're going to call training, the other one is going to be called validation. We use the training set to fit the model, and then we use the validation set to check the accuracy of the model. So we are computing the accuracy of the model on the validation set. This one is going to be used as an estimate on the accuracy on the test data. So this is going to be estimating the accuracy of the model on test data. But again, this is only one partition. We know there's going to be some degree of random error in here because we are randomly splitting the data in two. So the point is we should look for a way to reduce variability in here, to reduce the effect of the random partitioning. And we can visualize it here. So here we're plotting as a function of the flexibility of the model. Let's say we have a model of a certain polynomial relationship between a variable and the response. And in each of those lines, we represent the error of the model as a function of the degree polynomial, and each of those represents one split of the data. So you see, depending on which specific data split you use, you're going to have different results, slightly different results. And again, this is important because the split is random. So our estimate of the test error is going to vary too much. We also have to think about bias because the actual training set that we're using is smaller. We are not using all n observations for training the model. We're using a fraction of it. And therefore, this model that we are testing is going to be slightly worse than it could possibly be because we're just using fewer data points. We're not using all the data we have. So that's also something to bear in mind, that this estimation of error is going to be higher than it actually is. And then what we see is that the validation set, of course, could be overestimating the test error for this reason. So what we do to try to get rid of this variability problem is do something called k-fold cross-validation. This is one of the many ways in which we can do cross-validation. It's just the one that I'm going to tell you about. So the thing is that we split the whole training data set in k-folds of the same size, let's say 5 or 10. So from the beginning, we're going to split the whole data set in k parts, k-folds. And then for each fold, we're going to do the same. We're going to train the model on all data except that one fold. That's going to be the training set. We fit the model, and then we test it on the validation set, which is the fold number I. So the cross-validation accuracy is going to be the mean over those k folds. Usually, again, we choose k equal 5 or k equal 10, something like this. And this is going to be especially useful in prediction settings. Let me give you an example again. So let's say this is all the available data. This is n observations. For 5-fold cross-validation, for example, k equal 5, we randomly split in 5 parts, fold 1, 2, 3, 4, and 5. And then we do fold number 5. We set it apart. We call it the validation set. So we train the model on folds 1, 2, 3, and 4 together. We build the model number 5. And we test how well it performs on the validation set number 5, so on this part here. And that's going to be one measurement of the accuracy of the model in this specific split in fold number 5. Then we do the same with fold number 4. We train the model on folds 1, 2, 3, and 5. That would be our model number 4. And then we test the accuracy of the model on the validation set number 4, so on this part here. And that would be a different estimate of the accuracy of the model based on a different validation set. We do the same for the others, for fold number 3, 2, and 1. And we are going to end up with these 5 estimates of the accuracy of the model on a different data set, on a different test set. Validation set. So we have those 5. We compute the accuracy, the average. And that's going to be the accuracy through cross-validation. And that is going to be an estimation of how well the model behaves in reality over the population. And again, by doing multiple folds, we are going to reduce the variance in this estimation. So we have a question, but if you now do this partition again with the same data, but in a different partition, you still use the same data points, and some will still be in the training set, so those will have a slightly bigger effect on the model. Doesn't that give some complication? Let me read that again. If you now do this partitioning again with the same data, but in a different partition, you still use the same data points and some will still be in the training set. So if I understand correctly, what you're saying is that when we build the model here, we are using this data. And when we build the model here, we are also using the same data. And when we build the model here, we're also using this data. So those will have a slightly bigger effect on the model. Is that what you're referring to? This is not a problem because we have 5 independent models anyway. And the important thing is that we are testing on different sets. There's no overlap here in the test sets. What we do know that happens is that, as we said here, there's a certain degree of bias. We know that the model is not as good as it could possibly be because we are not using all data. But in principle, there's no problem for that. The problem is that, again, these are estimations that should be overestimating the error of the model. And if we want to get very, very technical, these are not independent models. Normally, when you want to do some statistics about the estimations and everything, you would have independent observations. But here, these 5 are not independent because they are all predefined from the initial split. There are ways to go around this thing. There are some corrections, but it's not something that we're going to talk about. So to show you what happens is here on the left side, we have, again, as a function of the degree of or the complexity of the model, each line here represents 1-fold in 10-fold cross-validation. So we see that there's a certain degree of variability in the results because we are having only one partition. So this is plotting only one of those. So in 10-fold cross-validation, if we look at the results, it would be something like this. There is a lot of variation. And we do 10-fold cross-validation, for example, or k-fold in general, to reduce this variation. And then we have something like this. Each of these lines corresponds to one full run of 10-fold cross-validation. So each time we do the 10 splits, we compute the 10 estimates of accuracy, and then we compute the mean of them. So we compute this mean over faults. And that's what we are plotting here. So you see the variance is reduced a lot. So that means you are expected to have a stable result for any run of 10-fold cross-validation in this specific example. You don't expect to have a lot of variation in here. So by averaging over multiple folds, we are reducing the noisiness of the experiment, of the splitting process. So this is what k-fold cross-validation is. And so it's giving us an estimate here of what the accuracy of the model is going to be. And based on this, we can make decisions about what the sweet spot is for a problem. So, for example, if I look at this plot, I would say that somewhere around here is fine. A polynomial degree of 2 looks like it's okay because it's the one decreasing the error. And beyond that, we are just adding complexity to the model. It's not going to change too much. So this would be a use of cross-validation. And it's important to remember, any decision whatsoever about the family of models to choose, about what predictors to use, about the complexity, anything, any decision about what the model is going to look like has to be made before observing any validation data. Before you look at what the data that you're going to test on looks like. Never look at the test data, the validation data. Because then you're making decisions based on what you're going to test the model on. So a typical wrong use of cross-validation will be something like, look at the full data set, do some preliminary analysis to select what the best predictors seem to be, and then do cross-validation to estimate the error. We know that that estimation of error is going to be underestimating the true error because you're making already decisions about the model based on the data that you're going to test the model on. And that would be cross-validation, to use an arbitrary measurement of the accuracy of the model. So you can compute the accuracy of the model however you want. This A can be anything you want. Now, there are general cases and general criteria that we can always use. And the two most important are based on information theory. So the point would be, given two models, so like in here, given two possible decisions about the degree of the polynomial, about the complexity of the model, we could compute these two coefficients. One is called the Akaike Information Criterion, AIC, And the other one is the Bayesian information criterion, BIC. They're very similar, and essentially they differ in whether they penalize for the size of the dataset or not. So the archaic information criterion, for example, is one of the most popular. What it looks like is, or what it looks at is, what is the probability of the data, the training data, given the model? So what is the likelihood of the model? So essentially, given all the training observations we have, we see how likely they are under the model that you are testing. And then the thing is, we are going to penalize complex models through this P, through the number of features in a simple case, or any arbitrary measurement of the complexity of the model. So we know that this can get arbitrarily high, but we're going to penalize by the number of parameters. So given any two models, we could always choose the one with the lower AIC. It would be the one with the best trade-off between the probability of the data given the model and the complexity of the model. Or we could go for the Bayesian information criterion, which is essentially the same thing, but it's incorporating here the size of the training data. So it's kind of incorporating the amount of evidence that we have in one or another direction. So again, this is just two general criterions that we can use to select the best of 2 or 3, 4, or 5 models. And they're based on the probability of the data under the model and the number of parameters. So it's a way of seeing whether, you know, we are getting a better and better model just by increasing the number of parameters. And hey, AIC and BIC are good alternatives because they're general and have nice theoretical properties. But the best measure of the model accuracy really depends on your particular problem. It really depends on what kind of data you're looking at and for what purpose you're looking at the data. So you always have to think about domain knowledge. In many cases, this is going to imply ad hoc measures. So for example, imagine that you're working on a classification problem. You want to classify images. You work in Google, you want to classify images and you want to classify, you know, cats versus dogs versus whatever animal. Maybe the only thing that you care about is whether you classify correctly a cat, and that's it. And you don't care about what kind of mistakes you make. Only you care about whether you are able to classify cats. On the other hand, you could be interested in never mistaking a dog for a cat. So yeah, you want to classify cats, but never mistake it with a dog, because some people are going to get mad at you. So you can always define accuracy however you want, depending on your problem. And if you don't have any indication that you should do one thing or another, then you can always choose generic measures like AIC. And for different statistical learning tasks, we are going to cover different measures that we use, generic for regression, generic for classification, but always remember that how you measure how well the model behaves depends on your specific problem. You can define any measure of accuracy that you like. And that was the end. So again, what we have covered here is the difference between supervised and unsupervised learning, what kind of problems do we build models for, and then how we specify the model, how we estimate it based on training data, and how we make selections from different models, cross-validation, test data, that kind of thing. And the importance of the various bias variance trade-off, because we can get arbitrarily complex models that behave arbitrarily well on training data, but then they're going to be completely useless because they are overfitting. So how to prevent from overfitting a model? As usual here, in the end, you have pointers for further research. I strongly suggest that you take a look at these two papers. One of them talks about the difference between explaining and predicting. So how is it different to build models for explaining data or for predicting in one specific problem? And the other one is about the two cultures of statistical modeling. So one more leaning towards statistics and the other one more towards computer science. Kind of in the same idea as the other paper, but I suggest you take a look at them and read more about it, because it's very important that you are aware of these two cultures, so to speak, whether you want to build very good models for prediction or for explaining. Again, what we are going to try to do in this course is try to build models for explaining. And then optionally, there's this Introduction to Statistical Learning book. I suggest you take a look at chapter 5.2 on Bootstrap. which is very related to cross-validation, and chapter 6.4, which talks about building models in very highly dimensional spaces when you have very large data sets with many features. So again, take a look at these two papers. And this was the end of the lecture for today, right on time. As usual, I'm going to upload the video to Brightspace once I have it in a few minutes. There will be a Q&A about this lecture next Monday. And in the meantime, if you have any question, I'm going to be here still for a couple of minutes to see if there's something. And if not, we'll see you Monday for the Q&A. Remember that you have the submission for the visualization lab this week. And there's not going to be any lab about this lecture about models. But anyway, it's important that we understand all these concepts for the upcoming lectures and labs on regression and classification. So again, I'm going to be here a couple of minutes if there's something, and if not, see you Monday.